Exercise 17E, antidifferentiation. As the name suggests, this is the opposite of differentiation. So if I've got a derivative, a gradient function, and I need to find what the original equation was, we need to do the antiderivative. So let's have a look at the process. Let us start with an example. Let's just say I have the equation y equals x squared. And what I'm going to do is I'm going to show a variety of processes. So if I was to do the derivative of this, we would take the 2 down and multiply it at the front, and then we'd subtract a 1 to get 2x. Now, what if I had that answer and I need to work my way up back to the original equation? Well, what we would do is we do an antiderivative, and we start by describing it with a particular symbol. And the symbol is called the integral symbol. So that weird looking S thing that looks like it's been squashed up there, that is the integral symbol. And you might also notice this weird looking dx at the end. What that means is that I am finding the integral, or I'm anti-differentiating with respect to x. Remember that dy over dx, it's the change in y with respect to x. This is again with respect to x, meaning that I'm only dealing with x's, no other letters. So when I'm anti-differentiating, I know that for this, I need to get to my original answer of y equals x squared. So what do I do? So I know that the original answer did not have a 2 at the front. So, and I also know that it's, instead of being x, it was x squared. So let's start with the power for a start. That might help us. So x would be the same as x to the power of 1. I know I'll have to add 1 to that. And we know we had this 2 at the front. So in order to get rid of that 2 at the front, because it's 2x, I would need to go and divide it. But divide it by what? I can't just divide it by 2, because that wouldn't make a formula, would it? I can't just say everything divide by 2. No. I would need to divide it by something. So, considering I put a 2 down, and that was the squared take away 1, that was that squared that we originally put down, wasn't it? So what about if I could say, divide it by that power? Yes, so what it was is I'm dividing it by the original power, or in other words, I'm dividing it by, in this case, the 1 plus that 1. And then I would, as you can see, so I have to add the power. So I'm dividing it by that 1 plus 1, or that power plus whatever the next one up is. Because 2 divided by 2 would be 1, and we get our original answer. Now, I will say at this point that when we're doing an antiderivative, we should also get in the habit of putting one little extra thingamajiggy, that's the technical term, and that's this little plus c fella. And the little plus c is just to indicate that there potentially could have been a constant. When we antidifferentiate, we can't always determine if there was a number at the end or not. For instance, as you know, if our original question was x squared plus 4, when I do the derivative, that would just become plus 0. So unfortunately, there's no trick way to know that, aha, there was definitely a plus 4 there. So we put this plus c just as a little reminder to say to ourselves, there might have been a constant, and we need some extra information to determine if this is so. So in general, the antiderivative formula that you have is that if I've got any x to the power of something, let's just call it n, that the antiderivative, I'm going to divide it by that power plus 1, and then I'm also going to add a power back to the original. There's a few little tricks and tips and tricks that we can also help ourselves with here. If I've got some expression, I've got something plus another thing, I can just antiderive them one at a time, much like we can with derivatives. Similarly with subtractions as well. The other thing that is possibly one of the most useful bits of fun factage is if I've got some number at the front of my expression, I can actually just plonk it outside the antiderivative as well, and it will equal the same thing. Example 1. Let's find the antiderivatives for each of these. A, 1/2 x cubed. So, as per that original plan or that original formula, I can actually take the half out of here. Then what I'll do is I'll do the antiderivative as per the formula. And then I will simplify. And there is our antiderivative. Now, I want to also go and do this exact same question without taking the half out and show you that you get the exact same answer. And as you can see, just by leaving it in, I get the exact same answer. So why would you bother taking that sort of factor of k or that number out? It just makes life a little bit easier. You don't have to, but that is just something to be aware of. It will be useful in year 12 when you get to the stage where you have to recognize antiderivatives, but this is just a little helpful tip for now. Let's have a look at the next examples. D, the antiderivative of 4/5 x cubed minus 2x squared dx. So I'm going to split that up into two antiderivatives and antiderive accordingly. I've always made sure to keep my dx's in there because that's grammatically correct. And what I'm going to do, just like I did in the previous example, I'm going to take those factors out. Once I've done that, I can do the antiderivative. We do not need to combine the fractions. G, let's have a look at this. This is the derivative of 2x squared brackets z minus 1 dz. So this time we have to do it with respect to z. I would suggest expanding it and then anti-deriving each part. And there's our final answer. You'll notice there that in this time, instead of putting the numbers in the denominator, I've just made a fraction at the front. It doesn't matter, you can have your answers in either way. You may also notice I did a small scribble. I accidentally wrote dx instead of dz. That is a common mistake a lot of people make. Please make sure that you get the right d whatevers, otherwise it's considered to be wrong.